Hi everyone, and welcome to the fourth video in which we are learning how to model an end plate steel connection. Today is another day, so I don't have ANSA opened anymore. And for that reason, let me open a new ANSA session. And I'm going to choose ANSA layout, click on OK. And in here you have the .ansa file that I want to open. Let's close this window, and I have shown to you how to open a file by going here in File and Open, right? But there is another more practical manner that we can do this, which is by going to the working folder, getting the file, left click and hold, and drag it to this position. And then the model is going to open. Well, in the previous video, we have finished defining the domain of the mathematical model. And today, in this video, we are going to discretize this domain, because we know that one of the first steps in the finite element method solution of the mathematical model is to discretize the domain, to split it into finite elements. And that's what we're going to do here. But before we start working on it, let's just do a quick overview of what we have here in this database. It's very important to keep complete control over what we have in this database. Okay. But before we do this, select here the classic topo module, because depending on the module that we have here, sometimes the structure of the database changes. So let's start with this first item, properties. It's in the FE structure group. We have 9 properties defined, which are all shell sections. And in here, for example, this one has the material, thickness, element type, and the property ID. We have the materials that we have defined. So far we have 2 materials. In this video, I guess we are going to have time to finish setting up the material properties. We need to define a plasticity. And then we have faces inside the geometry group. So we have all these faces that we have created. We have this one, this one, this one. Oh, looks like this face here is not correct. This face, this green face here, it's not supposed, well, we should have it splitted in this region. Let me show you one important tool that I use to check if everything is correct with the cons and connections between faces. Before we do this, let me activate the visualization of double cons by clicking here. And in your ends, I guarantee that you have the same options activated here, so you see the same thing I am seeing here. Okay. Now, if I hold the Control and Shift buttons together, well, for some reason it's not okay. Control and Shift button together, I'm holding it. I can have this visualization mode activated, and let me deactivate the visualization of points, because it's not really helping, and also curves. I don't want to see curves and points. And now I'm going to hold Control and Shift, and in here I can easily see the cons, right? So C and cons are connected to 3 or more faces. Red cons are connected to only one face. So you see that the red cons are in the perimeters, in the outer perimeters of the faces, and they are isolated. And the orange cons are cons that we have eliminated, and we have it here just well, it's not really a cone anymore, but We have it here just to remind ourselves that we had a cone here before, and we can get it back if we want to. The yellow cones are double cones. They are connected to exactly two faces. Okay. Now you see that we have this yellow cone here, but we are supposed to have a cyan cone here, because this cone was supposed to be connected to 1, 2, 3, 4 faces. Let me show. It was supposed to be connected to this green face on this side, to this green face on this other side, to this face, and to this face. But this is not really the case here. So let's use in the classic topo module the project tool, project inside the cones group, select this cone, middle mouse button, and select this face. And guarantee that you have activated here the paste option, and then middle mouse button. And now hold Ctrl and Shift, and you see that now we have a cyan cone here. And if I go to double click on faces, now this face goes up until this cone, and then we have this smaller face here. And then we have, so you see that this cone is connected to this face, this one, 4 faces. Okay. All right. Now hold Ctrl and press ESC to deactivate all functions. Hold Ctrl and Shift, and let's look around this model to see if everything is okay. So we have this yellow one because it's connected to 2 faces, these 2, and cyan connected to 3 faces, and the red ones are in the outer perimeters isolated. So let's look around, and in here looks like everything is okay. And also here, only cyan and red cones. And in here we have these double cones because we have these divisions. So everything looks okay now, and we can continue. So in the database, we were in faces. We have also the cones. We have the hot points. You see that we have 1 hot point in each corner. And you're going to eventually understand more about hot points when we get to work with mesh. Not really so much in this tutorial, because the mesh here is going to be pretty simple, but maybe in future tutorials when we get to work with more complex meshes, you're going to understand more about hot points. For now, just think that these are points positioned in the corners of the faces. We have this center entity. It's not really so important. It is in the center of the holes. Curves, points, ANSA parts, and we have the ANSA parts very well organized, and then working planes. Okay. All right. So let's then work on this mesh. To work on this mesh, we are going to go to a different module. You see that we have 2 modules here related to mesh, one named mesh and the other named volume mesh. Depending on your ANSA version, you might see something different here. Maybe you see only one button here related to mesh, but that's okay. What I want you to do is, if you see it like this, click on this drop down list, and then you're going to see these options. And then the one that I'm going to choose is classic mesh. Okay, but if you don't see it like this, try to search for classic mesh, use some drop down list that you see, or search these buttons here. Look around these buttons here until you see the classic mesh module. And then when we do this, we have new tools here that we can use that are related to meshing. Just 1 second, guys. All right. So the first thing that we need to do is to define the element size that is going to be used here. Well, for models like this, I usually use an element size equals 5 millimeters. I know that for this element size, the mesh is going to be converged. We don't need to even perform a convergence study for the mesh. Obviously that you can do this if you'd like to, but from my previous experience, I know that for this kind of model, for a model of this size, the mesh is going to be converged for an element size equals 5 millimeters. Obviously, considering that we're going to use the element type S4. If we had a different element type that is not so good as S4, then maybe this is not true. Okay, so this is the first thing. And you see that if we zoom in, we have these white dots in the corners. These are the hot points. But in the classic mesh module, the hot points become white, these white dots. If I go back to the classic topo module, you see that the hot points are these green dots, right? But in the classic mesh module, it becomes these white dots. Now, you see that we have these pink dots along the edges. These are the perimeter points. And this defines the length of the elements. Where we have these pink dots, we are going to have nodes generated. Okay, it's not only this that defines the size of the mesh. We should also change something here in the mesh parameters. Okay, but before, let's work with the distance between these points. We can use the measure tool here, and then I want to select here dynamic selection mode, zoom in here, for example, and measure the distance between these and these. And then we have a distance equals 10 millimeters. Okay, by the way, since we have created this geometry using millimeters, obviously that these measures are in millimeters. Now we need to adjust this. And to adjust this, you see that there is a perimeters group. And we have this function here, length. Alter shell element length. Left click here. And then in the selection window, I'm going to select by perimeters. So if I select by perimeters, I can select the cons. And if I select macros here, I can select by the faces. So in the classic mesh module, macros is the same thing as faces. Okay, it's just a different name. Actually, in here, it's not going to make so much difference if we choose macros or perimeters, because I want to select everything, creating a box selection using the left mouse button, and then middle mouse button to conclude this selection. And then in here we can define the length, and then in this case I want to define it as 5 millimeters, and we don't need to worry about these other options. Click on OK. And now if I zoom in here again and use the measure tool and measure the distance between these and these, you see that now the distance is 5 millimeters. Okay, so now it's correct. Okay, so but we need to do something else to define the length of the elements in the macros, because what we have done here is, well, we have defined the distance between the nodes along the cons or perimeters. Okay, another name for the cons in the classic mesh module is perimeter. But now we need to define the length of these elements in the middle of the macros or faces. And to do this, we are going to click here in this button, this yellow button, Mesh Parameters. You can also find it in Utilities menu, and then in here we are going to have the mesh parameters, or you can search here, mesh parameters. Click, and then it's going to show where this tool is positioned. Okay, now, there is a lot to learn about mesh parameters. In here we can set up many things that is related to something that we name as batch mesh. Again, in the ANSA meshing course, I teach everything about this. But in this simple mesh, we should only look at a few things. You see, target length is one of these things. In here, we should set it as 5, and then we define the length of the elements in the middle of the macros. And then in here, we have these algorithms that this is related to the algorithm that is going, not really related to the algorithm actually. Depending on the option that we choose here, we are going to have some fields with a different standard value. It's not really so important. In here we can select general, and in here, well, this part is really, really important. When we are dealing with shell elements, we should always choose mixed here. You know that we should try to avoid triangles in a shell mesh, because triangles are not good. You know, shell meshes are linear elements, right? We have, for example, for the quadrilateral element, we have 4 nodes, and for the triangle, we have 3 nodes. For that reason, and we also know that in the formulation of the shell elements, we have a mix of the plane stress element and the plate element. And for example, if we have a triangular shell element, the plane stress formulation that is used is the constant strain triangle, which is not a good kind of element. So we should try to avoid as much as we can triangles in the mesh, but it's not possible to avoid all triangles. I'm explaining this because, well, maybe because of this explanation, you would like to choose this option, quadrilaterals, so that the software is going to try to force only quadrilateral elements in this mesh. But it's not a good idea, because then we are going to have one problem occurring, which is we are going to have 3 quadrilaterals sharing the same node. Actually, it's easier if I create a drawing about it, because this is an issue that we should avoid. And it happens if we choose the quad option. Let me get my pen. If we choose the quad option, something like this happens a lot in the mesh. We're going to have like one quadrilateral element here, another quadrilateral element here, and another quadrilateral element here. And then you see that we have one node that is connected to exactly 3 quadrilateral elements. And this is not good numerically. We should avoid it. Obviously that it's okay to have something like this. And then we have one node here and 4 quadrilateral elements sharing this same node. But when we have exactly 3 quadrilateral elements sharing the same node, then this is not a good thing. It's not good. It's going to yield to numerical errors. Okay, so for that reason, I don't try to make the software force the creation of only quads. Obviously that we're not going to use trias here as well, We use trias or orthotria when we want to create a mesh that is going to be used later to generate solid tetrahedrons. Okay, we're not going to learn in this tutorial about it, but maybe in a future tutorial when we get to deal with solid elements, tetrahedrons, solid elements, then I'm going to show these two options. Okay, so we're going to choose mixed. And what the software is going to do is it's going to use quadrilateral elements where it can, but when we have a more complex region, it's going to mix some triangles in the mesh. And that's okay, because there is going to be just a few triangles anyways. And then in here we have first order and second order. For shell elements, we should choose first order. So that we are going to have the S4 elements. We also have second order shell elements. It's used in some specific situations, but we know that the S4 element, which is a first order fully integrated shell element, is a good one because it can be used for thick shells, thin shells, and anyways, it's a very good kind of element. Okay, so first order, mixed, 5mm, and that's all we need to define here. Okay, click on OK, and let's define the quality criteria that is going to be used. This is very, very important. Since FEM is a numerical procedure to solve approximately a mathematical model of the type boundary value problem, we should try as much as we can to reduce the errors introduced by the solution. And one of the things that we do is to use quality criteria to create the mesh. And then to establish these quality criteria, we have this button here, quality criteria. And then you see that when I open it, we have all these options here in the shells tab. We also have the solids tab and these other tabs, but the one that is going to matter here for us is the shells tab. So remember in Abaqus, in the Abaqus exercises, that we didn't have so many options like we have here. So that's why a preprocessor software is the one that is actually used in the industry and not Abaqus CAE application, because Abaqus CAE application is very limited, and in here we have much more advanced tools for preprocessing. While in the ANSA meshing course I explain in details about all these quality criteria. In here, we are not going to have time to do this, but if you position the mouse on each one of these quality criteria, you can see a description. It's pretty easy to understand, actually. Well, what I'm going to do here, guys, is you don't need to do what I'm going to do now, okay? I'm going to open another ANSA session. Please just watch what I'm going to do now. In here you have this file, the .ansa qual, that has the quality criteria that we are going to use. Just for you to understand how it works in the industry, if you get to work in a big company, they are going to have in their database many quality criteria files that is applicable for some kind of analysis. In this case, this quality criteria is used for durability analysis, and where the target length is 5 millimeters and minimum length is 2 millimeters. But in big companies, you would have a database for example, I want to perform a thermal analysis. Then I'm going to use this file of quality criteria. I want to perform a dynamic explicit analysis. Then I'm going to use this other file, and etc. So in reality, we don't always define from scratch these parameters. We usually import a file. But maybe it's the first time that you are seeing this, so I don't want to import a file that is ready. So what I'm going to do is, in this empty ANSA, you don't need to follow this part. I'm going to import this file here in this empty ANSA. And to import it, I simply click in read quality criteria data, navigate to that folder, and then get this .ansa qual file. And then I'm going to have everything ready here. And just to practice, we are going to define these quality criteria based on what we have here. Okay, just for you to see how it works. So I want to use aspect ratio, and then we have here the calculation methods. So we can choose between all these calculation methods. Each software or solver uses a different calculation method. In this case, I'm going to use the Nastran calculation method. And then in here we define a value, which is the threshold for this to fail, which is 5. So again, position the mouse like this, and then you're going to see how this is calculated. It's just the largest size divided by the smallest size. And then we can't have this ratio larger than 5. That's the meaning of this. It's pretty easy. Now I'm going to have skewness activated, so check this box. The calculation method is patron, and the threshold is 45. Now also warping is very important. Ideas, and then the maximum is 15. Now let me see Jacobian. This one is very important. We have learned about the singularity problem, right? So that's why it's important to have Jacobian activated. By the way, we have learned in the theory part of this course how this is calculated, and we also used it in previous exercises. So ANSA calculation 0.6. And then mean length and max length. So the minimum length that we're going to allow is 2, maximum length 10. Okay, so if we have an element with a length less than 2, then it's going to fail. Mean angle quads and max angle. So 10, 45, 130, 10, 45, 135, and 20. Okay, so this is simple. Mean angle quads is the minimum angle allowed for quadrilateral elements, the minimum internal angle, and max angle is the maximum internal angle allowed. And mean angle trias and max angle trias works like that as well. Okay, so it's important to control these. The calculation method is ideas. Okay, so let's see the next one. Yep. The next one is triangles, 5%. So this one is important. When we activate triangles and then establish 5%, the software is going to tell if we have the number of triangles less than 5% or not of the total amount of elements. So as I mentioned, we should avoid triangles. We should, but it's not possible in complex parts of the geometry. We are going to have triangles. So what matters is to keep as the amount of triangles less than 5%. Okay. So it's important to have this metric. Now, after doing this, if you don't want to keep always defining these for all meshes that you're going to create, you can save this file. And then I'm going to save this. I'm going to give a name such as 5mm quality criteria. And then I'm going to save. And then the file is going to be here. Oh, here. And then in another module, I could simply open it. Okay. So just one last note. In big companies, what people do is for specific kinds of analysis and specific sizes of models, they perform convergence studies to check what is the element size that they should have and what are the best quality criteria that they should have, the best thresholds. And then for when they do this, they don't need to keep performing convergence studies in their meshes. I have mentioned this previously, but now I'm just reinforcing that the quality criteria works like that as well. So they perform studies about the best numbers that they should have here for a specific kind of analysis, and then you don't need to worry about it later anymore. Okay. All right. Now let's save this because we have done quite a few things, and now it's going to be easy to generate this mesh. To generate this mesh, you see that we have this group here, mesh generation. And we have many different algorithms that we can use to generate this mesh. This is something that I explore in the ANSA meshing course. But in here, what matters is that what we're going to usually use is this one. If I click here on this drop-down list, I can see more options, and I want to find this one, best. Maybe the best tool is positioned in a different place. Maybe it's positioned here and not in the other tools. So try to find the best tool. And this one, the description is mesh macros using all alternative algorithms and keep only the mesh of the best quality. So the thing is, the software is going to try different algorithms in the macros that we're going to select, and it's going to keep the best mesh of the, well, it's going to keep the mesh, the best mesh of the between the algorithms that were used. Okay, so I usually use this option instead of trying to select the best algorithm here. Okay, so left click and hold until you see these options, and then I want this option here, select. And then in here you see that we have some options, right? So the element type is mixed because we have defined it here in the mesh parameters, and it's not a second order, so do not activate this. And we have this other option here that I'm not going to talk about now. Now, if I zoom in, for example, here, and left click on this and middlemost button, you're going to see that we have the mesh generated here. But obviously that I'm not going to do this macro by macro. I'm going to zoom out, select everything, and middlemost button. Now the mesh has been generated everywhere. You see, and the mesh is looking pretty good. And one thing that we should notice is that since we have connected, for example, this face to this face by projecting the cone, we have a continuity in the nodes of this mesh. So for example, this node is part of this element, this one, and this one. So this node is part of elements of this purple face and this gray face, which means that these two faces are connected through the continuity of the nodes. And that's how we are representing the weld that we would have between these plates. Okay, now the next step is to treat the mesh around these holes. Because at least around the holes, it's a good idea to try to keep only quadrilateral elements. Okay, it's a good practice. And for this to happen, we create something named as washers. Okay, so let me show you how to create the washers. The first thing that we should notice is that when we created these holes, remember that we clicked on the center of the hole, and then we clicked on a line that was horizontal. And then because of that, we end up having a hot point here and a hot point here. So the position of the hot points is organized. If we had created the circle, for example, clicking here and then clicking here, then the hot point would be positioned here and here. And then this is not good for mesh quality. Okay, so now you see one of the functions of a hot point. A hot point is a position that we are going to have a node of the mesh. Okay, so you see that for all holes we have the hot points in the horizontal direction, and this is good. And now let's create the washers. To do this, there is this button here, this one, features. Left click in features, and there is nothing here. So we should recognize the features, and holes is one kind of feature, but we have many other kinds of features. To recognize, we go to parameters, and then you see that we have holes 2D, which is this kind of feature, but we have fillets, chamfers, stamps, flanges 2D, and etc. So the idea here is that the software is able to recognize many kinds of features, and then after that we can apply some specific treatments to these features. And this is something that we learned in details in the ANSA meshing course. In here we're going to learn just what we need for this mesh. So what we need here is to check this box so that the software is going to recognize holes 2D. And we can also have these other boxes checked. It's not going to make any difference in this case. Now click on, notice here in this region of the holes, click on recognize, and notice that we have these as yellow lines, which means that the software has recognized these features. Now we can click on OK, and you see that we have this list of holes in this window. Okay, each one of these items is related to one hole that we have there. You see that when I go to this item, this hole is highlighted. This is because I have this option activated, pick. Okay, if I don't have this activated, then it doesn't highlight the holes in the drawing. So let me activate pick here. Okay, so the next step is to apply the treatment itself. So let's for example apply the treatment to this one. I'm going to select this item here. You can select any hole in your model because I just want to give it as an example. And then you see that we have these 3 dots, right? Click here and then select. And then you see that, well, we have a table, right? In this table, for example, this column is related to the diameter. So it has calculated this diameter as 21.98. We had defined it previously as 22, but in here it's calculating it as 21.98. It's okay. This last column is named as treatment. And these 3 dots is to create a new treatment. So left click here, and then we can see a list of treatments available, but we don't have any treatment so far, so we need to create a new one. And then, for example, if I click on this option, the featuring, and you see that we have these options here, right? If I click on fill, then the treatment is that it's going to fill this hole with elements. I don't want this. So let's deactivate the featuring. And then nodes number is related to how many nodes we're going to have around this hole. I'm going to activate it, and then I'm going to let the auto option, the automatic option, that is going to calculate the number of nodes based on the element length that we have defined. But we can also select here an expression, and then, for example, I can define this first parameter, if I'd like to define the whole perimeter node's number. So if I click here, and then instead of auto, I select 10, so n equals 10, this means that I'm going to force 10 nodes around this hole. But I don't really want to do this. But you see that we have other options here. You can check it out. I can define it by the whole diameter size, for example, or anyways. Let me cancel, and I'm going to have the auto option here. And if it doesn't work well, we can try some other thing. We have this option here, treat as round. This is the case when we have holes with this shape, which is not our case. And then this is the important part, zones. Zones are the washers. Okay, if I position the mouse here, I can see this drawing, and then you see that we have these blue lines that is related to zone 1. And the zone 1 has this width W, and we have the red lines that is representing zone 2. And anyways, in this representation, we have 2 zones. In our case, we can do 2 zones as well. Let's try. So activate zones, and then in here we have the first zone to define, and we can define the width. I'm going to define the width to be equal to 5, because this is the element target length. Okay, so if the width is equal to 5, the width is going to define the size of one of the elements, right? And then I can create another zone, a second zone. And then when I click on this plus button, this new row appears, and then the second zone can have a length a little larger because it's going to be in a larger diameter, so maybe 6. Okay, and I can create more zones if I'd like to, but usually 2 zones is good enough. And if we don't have a space, we can create only 1 zone. Okay, and here we can activate to define a target diameter if we'd like to. So if we want to force the 22 millimeters for the diameter, we can select this option, but I'm not going to do this in this case. So simply click on OK, and then this appears, apply treatment, and then yes. And then because it's going to create this washer, the software is going to reconstruct the mesh around this hole. So you see that these elements are selected automatically, and this function here shows up, the improve function. This is a function that we can activate manually as well. Okay, and then now we have these options here. It's going to reshape, and then we can go to next. We can click here or use the middle mouse button. And then in here we can select these edges here that are in the boundary, these white edges here, we can deselect. It's not allowing me to deselect because I need to go here and I need to allow the deselection. Anyways, but there is no need to actually deselect. For example, if I select this edge, then when we do this, and when the improve function works here, it's not going to allow this edge to be modified. But I don't really want this, so I'm going to deselect by right clicking here. Go to next, and then you see that it has created the washer, and it's looking good enough. We have space even to create more washers if we'd like to. What I don't really like is the width. I think that the aspect ratio is not so good here. You see the ratio between the largest side divided by the smallest size is too large. Obviously that we're going to check the quality criteria shortly using a function that I didn't show yet. But anyways, I want to modify this. So I'm going to right click here, mesh treatment, and then edit. And then I'm going to decrease this to maybe 4 and then this one to 5. And then click on OK. Yes. Next. Next. And I guess this is looking better. Okay. I guess the aspect ratio is better. Yep. I guess this is looking good. Yep. So now I want to apply, and then you see that in this column we have washer and we have this checked, which means that for this hole we have a washer with 2 zones. And we have only quads around this hole, which is a good practice. Okay. And this is a good practice. One of the reasons is because usually we have high stress around holes, and so it's a good idea to have good elements around holes. And also because we're going to create couplings here. Actually, this is the main reason, because we're going to create couplings here shortly. Okay, now I want to create this washer for all holes at the same time. So I'm going to select one item of this list, Control A to select everything, or you can select the first one, scroll down, or actually we don't need, hold the Shift button and then select the last one. And then right click, mesh treatment, list, and then since we have created this mesh treatment for this one, we have in this list the mesh treatment that we have created. Click on OK, yes, next. You see it's going to reconstruct the mesh around all these holes, next, and we are finished. Now let's close this. And we are almost finished with the mesh. We just need to do one additional thing, which is to check if the elements are meeting the quality criteria that we have defined. And then we have this tool here. We have these buttons here. I guess it's the first time that we're going to talk about it, right? And by the way, I should have explained one thing to you before. You see that we have this draw mode, right? This draw mode is related to how the parts are going to be painted. We have PID selected. So the parts are going to be painted as per their PID colors. So if I go to the property list, each property or PID has a different color, right? So for example, this one is related to this part, and it's green because we have the green color assigned to this PID. Now, if in the draw mode I change it to MID, then the parts are going to be painted as per their material. So you see that we have the material list, we have 2 materials. This one is using this color, and we have all these parts with this material, and this one is purple, and we have only these parts with this material. Okay, so let's choose here PID. And you see that we have this button here, hidden. If we click here, then this list is going to show up. And by the way, you should be in the classic mesh module now. And then here we have many quality criterias, and but just some of them are activated. These ones are that we have this rectangular rectangle to the left. I don't want to show the quality criterias that we are not using, such as taper, crash, and etc. So right click here and hide inactive criteria. Now I want to move this to the left. So position the mouse here, middle mouse button, and hold. And then you can position this in this corner. And now you see that we have this other list. This list shows how many quads we have in this mesh, quadrilateral elements, how many trias, and how many total elements we have. We can also check this in this item, which is a new item in the database, element, expand, and then we have shell element, expand, and then we have quad and tria. And then in these columns, we have the quantity of quads and trias. Okay, so we have just a few triangles. It's less than 5%. So anyways, in this list, each quality criteria is related to a color. So if there is an element in the mesh that is not attending the quality criteria, then this element is going to be painted as per these colors. And also, if we had any elements not attending, we would have in this case, we don't have any element not attending the quality criteria. But maybe in your case, you might have some element not attending. So I'm going to simulate here a situation that I don't have an element attending. So I'm going to go to the classic mesh, and I'm going to use the move tool in the grids group. Grids is the same thing as nodes. Okay, so I want to move a node. Move tool, and then this appears. I want, let's go to the free tab. And I'm going to, let me actually go to the surface, this guided tab and surface option. I'm going to select this node, for example, and I'm going to move it like this. When we have the surface activated, the software moves the node in the plane of the surface that this node is defined. So it's going to recognize this plane of this triangle and move it in this plane. And you see that I distorted this mesh, right? And because of that, these two elements are not attending some quality criteria. It's painted in orange. In this case, it's not attending the angle quality criteria, which is related to the orange color. For example, if I move this node like this, now these two elements are not attending the minimum length quality criteria. It's painted in red because this side here is too small, right? Okay, let's see, for example, the aspect ratio. I'm going to move this one like this and this one like this. Let's see when we're going to fail. Let me stretch it like this. Okay, it's not being so easy to fail due to aspect ratio. But anyways, I guess you got my point. So let's suppose that we have all these mesh like you see here. It's not really looking good. So I wanted to improve the mesh here. And then I have this tool in the shell mesh group. In this group here, I have this tool here, improve. If you don't find it here, try to find it in this other list, in this hidden list. Okay, we can use the reconstruct tool or the improve tool. They work in a very similar manner. So activate this. And then I want to select the elements of this triangle. So let's learn about a new tool. In here we have the selection filter, right? So I can select by PID, by angle, by entity. The entity option is activated. So I can select one single entity. So for example, one single element. I don't want this. One thing that is going to facilitate is to select by feature area. So if I activate this, I can define an angle such as 40 degrees. And if I select one area here, left click, it's going to select all elements that has an angle less or equal 40 degrees. to this element that I selected. Okay, and then it selected this whole area. Now, next, or use the middle mouse button, and then next again, and okay. You see that the software improved the mesh in this whole region. Okay, so in your case, if you have any region that the quality if you have any problematic region, just use the improve function in this region, and until you have it all right. And let me Control Z just to show another thing. You see that I have these elements here off, right? When I have these elements off in this list here, and I can also move this list if I position the mouse here, middle mouse button and hold, and then move it like this. I have this new item off, and then 6. This means that I have 6 elements off. In your case, if you have any elements off showing up here, but you are not being able to find it, then position the mouse here, right click, and then show only. And then it's going to show the macro that has these elements. And then I can go to improve, select these using feature angle, or since we have only, let me deselect to show, since we have only this entity here, I can select by entities and create a box selection, and then middle mouse button again and again. Right, now let me click here in show all, and now we have a different issue. We have some triangles here painted in green. This is interesting because this means this is related to this quality criteria, percentage of triangles. If we have the triangles painted in green, this means that we have more than 5% of this mesh in triangles. But this doesn't look correct because we can test it out. How many elements do we have in total? Let me get the calculator. We have this amount, 136, 217, right? Actually, let's get the number of trias, 207, and divide by the number total number of elements, 136, 217, and then multiply it by 100. We have 15% of triangles. No, this is not correct. Let me do this again. 136, 217 multiplied by 100. Okay, 0.15. Yeah, it doesn't make any sense to do 207 out of this number to be 15%. So we have just a few triangles. But this quality criteria is saying that we have more than 5%. It doesn't make sense. So it's not working correctly in this case. Let me go to the quality criteria. And then here you have 5%. Let me change it to 4, apply, and then 5 again. Okay. Okay, now it's not showing anymore. It was some kind of bug. I don't know. All right. So the mesh is ready. And it's looking good. Let's save this. We have a total of 136,217 elements. So it's not a small element. Okay, but any normal, any standard laptop can run this. You don't need to have a very good laptop to run this. Okay, you can have just a standard laptop, because nowadays the computers are pretty good, even the simplest ones. All right. So in this database, let's analyze what we have well, we have some additional stuff here, right? So you see that we have this element item. We have explored this element item already. And there is one interesting thing here. That is, for example, I can double click on quad. And then when I double click on quad in the database, I activate a filter in which I can only select quadrilateral elements. So if I try to select a triangle, I will not be able to select it. But if I try to select a quad, I can do this. So I select it, and then this is going to appear in this list. And then I can double click on this, and then it's going to open the card of this element. And then in here we have the type, which is quad, because it's a quadrilateral element. We can have quad or tria. We have the ID of the element. We have the property ID of the element. So if I select this property ID and press F2, I go to the property card, which is the end plate rib stiffener. And then in here we have the thickness defined, material, and type. I can click on OK to go back to the element card. Here we have the ID of the nodes that define this element. So we have 4 nodes. If I select one of these nodes and press F2, I open the card of the node. Here I have the ID of the node, X coordinate, Y coordinate, and Z coordinate. Click on OK, and then we are back in the element card. And then in here we have this very interesting field, which is thickness. So one thing that you probably haven't seen before, at least for my students, we didn't see this before. We can define the thickness for shell elements by defining the thickness at each node. So we can have a shell element with a varying thickness. Imagine a shell element with a different thickness in each node. So we're going to have something with it. Well, it's not going to be a uniform thickness. I don't really use this option. But when I'm dealing, for example, with plastic parts that has the thickness varying a lot, sometimes I use this option. Okay, but I usually define the thickness through the property, which is the case here. So I have the thickness defined in this property here as 10 millimeters, and it's a uniform thickness throughout the whole element. All right, notice here in the title that this is a shell element card, ends as 4. Here we have the nomenclature of this element, as we know, as 4, the 4-node fully integrated shell element. Click on OK, and just also remember that when I say fully integrated, just to be technical, I'm talking about the number of integration points that we have for this element. And we have 4 integration points in this case to characterize a fully integrated element. And remember that I'm talking about the Gaussian quadrature procedure that is used as a numerical integration procedure to calculate the stiffness matrix of the element. And we need to use integration points in this numerical integration procedure, which is the Gaussian quadrature procedure. Okay? And then when we have a fully integrated element, we have some specific characteristics assigned to this element, as we know. All right. Now we have property, material. There is nothing new here. The rest is, we actually have this new item, edge. So edge is the edges of the element. You see, for example, this is an edge. All right. We also have this item features, which is the holes 2D. Double click here, and then you see that we have a list of the holes that we have. Okay. My point is, everything that we create appears in the database, so that's why it's so important to keep complete control over what we have in the database. All right, let me see. I don't know if this is long enough. Yeah, 30 minutes, but this is going to be attached to the other video, so 1 hour. So there is no time to show much more in this video. Let me just show one additional thing here. You see that we are in the hidden mode, where we have the elements painted as per their quality criteria, right? Let's deactivate this, but if I simply click here, then this weird visualization mode is going to be it's going to be activated. You see that we have only the visualization of edges, but not macros. To visualize the macros, we should activate this option here, shadow. Now we see the macros or faces. Okay. Also notice that we have this new item, node. Double click here, and then when I double click here, I create a selection filter, and then I can select nodes in the module. So for example, I'm going to create a box selection like this, and then I'm going to have all these nodes selected, and then it's going to show up in this list. I can, to deselect these, I can left click on this blank space, and then select only one node, and then we can open the node card, and then we have the coordinates of this node and the ID. Okay. All right. It's not really worth it to start anything now because I don't have time. In the next video, then we are going to create the bolted connections. So we're going to use coupling here, and a beam element connecting. Actually, we need to put a connector here to apply bolt pretension. So there's going to be something more here. It's going to be interesting. It's a bolted strategy, bolt modeling strategy that is very, very important and used a lot. So we're going to create it. We're going to create the contact between the green face and the red face. We're going to create the boundary conditions, definition of step, and etc. So it's going to be a very, very nice lecture, and it's going to be very theoretical as well, because we are going to remember about many things that we have learned. Guys, actually, there is one important thing that I forgot. I wanted to show to you how we can visualize the thickness of these elements. To do this, we should go to mesh parameters, and then in the, sorry, not here, in the quality criteria. It doesn't make much sense that this tool is in here in quality criteria, but it is. I don't know why. And then in here, let's go to the last tab, presentation parameters. And in here we have this option, draw shell as solid. Activate this draw shell as solid and click on apply. And then you see that we are going to have the thickness representation of the shell elements. Click on OK. And this is very important for us to check if everything is okay. So for example, in here in this region, I don't want the elements to penetrate, because then we're going to end up having convergence issues with the contact definition. Not contact definition, but with the contact convergence in the model. Looks like it's all right in here. We can visually see that it's all right, but we're going to also run a check. There is like a check here, a checks manager. You see, we can run many checks here for Abaqus before we run this model. I'm going to talk about it later. Okay, so you can look around and visualize the thickness of the element. Everything looks okay. So you see that we have assigned the thickness to the face, and we created a mesh on the face, and because of that, the thickness of the shell that is defined on this face is the same as the thickness of the face. Okay. All right, so that's it that I had in this video, and see you in the next lecture.